recent simulation results about obtained for confined granular flows. So I would like to mention the people who contribute to this work. So my colleague from Rennes, Patrick Richard, Renaud Delaney, Jérôme Crassou, and also a PhD student from Rennes, Jean-François Métayer, and a former postdoc, Paul Sanchez, and also Nicolas Terberlet from Lyon and Michel Louche from Cornell. Sorry. So, I'm interested in the simple following configuration. We just pull some grain. We just put some grain in a hopper to have a control flow rate, and we let this grain flowing down two flat frictional walls. And after a transient where a heap form, you have a fully developed steady granular flow above the heap. Experimentally, you can tune the flow rate of the grain and also the channel width. And the angle of the heap, in fact, adapts to the flow rate and to the gap W between the plate you choose. This simple flow configuration is interesting in two aspects. First, you have an erodible boundary between the liquid-like phase and the solid-like phase, and you can have mass, momentum, and energy exchange between the solid and the liquid phases. The second important aspect is the friction of the lateral wall, and we will see that the friction plays an important role in the flow. And despite this configuration is very simple, quite few studies have investigated this situation. I just mentioned some work here. And the main motivation of this work is to understand the role of the sidewall friction. And also this is a sample system which exhibits a coexistence between solid-like and liquid-like phases. And we know that in this region we'll have a quasi-static flow where the rheology mu of I doesn't apply. And a number of questions can be addressed relative to the solid-like phase. Is the grain in this phase are really at rest or not? And we will see that the dynamic in this solid-like phase shares some properties with a glassy system. I would like first to recall you the main feature of confined flows, experimental features obtained by Nicolas Terberlet. So the results are the following. So we can measure easily the angle of the heap as a function of the two experimental parameters, that is the flow rate Q and the gap between the sidewalls. So we can see for a fixed W, if we measure the angle of the heap, it increases with the increasing flow rate. And we can see that we can obtain very steep angle of the heap, much larger, much steeper than the classical angle of repose. And also, if we change the gap between the wall, so the angle decreases with increasing the gap of the walls. So we can replot this data using other variable, and we get a nice collapse of the data
if we plot the data, if we plot the tangent of the inclination angle as a function of the height of the flow, h, divided by the width between the plates. So we have a nice linear behavior. And the tangent of the inclination of the hip, so it's just a linear function of the ratio between h and w. And the slope of this curve can be interpreted as an effective wall friction, and the intercept with the vertical axis as an internal friction of the granular material. And we call this equation SSH equation, just to remind you that this is SSH is for super stable hip or sidewall stabilized hip, because we can obtain angle much larger than the classical angle of repose. So is it possible to predict or to derive this behavior from simple argument? The response is yes. We just write the momentum balance for the flowing layer, and we make a balance of the different forces. We have the shear force of the static hip on the flow layer. We have the normal forces, and we have the weight of the grain. And of course, as the flow is between two flat frictional walls, we have an effective friction exerted by the wall on the layer of grain. So if we write the momentum balance, we end up with this equation, just the ratio of the shear to the normal stresses, which equals the tangent of the inclination, and we have an additional term due to the friction of the wall. Can we simply write the friction of the wall? Yes, if we make some reasonable assumption. If we assume that the packing is uniform throughout the flow, and that we have solid friction at the wall, characterized by a friction mu w, we can show easily that the friction force is, of course, proportional to the normal force times the friction coefficient and times this rescale height of the flow. And if we use a stability condition for the hip, that's the ratio of stress at the boundary between the flow and the static hip, it's just the internal friction of the granular material, we end up with the equation we just derived experimentally. So everything seems going nice, but if we put this simple model further, we end up with a paradox. In fact, the balance of the momentum equation can be written at arbitrary depth. Sorry. At an arbitrary depth. And we end up with the following equation. We have just a ratio of stresses, which is always equal to tangent of the inclination minus the contribution of the friction, which is now the ratio of the height of the depth divided by W. And if we go deep into the pile, so we arrive at a situation where the ratio of the stress should vanish and reverse sign, which is, of course, not physical. So to try to solve this paradox, so one possibility is that the assumption we made, for example, for the friction, a constant friction coefficient on the wall, is not true. So one of the possibilities is that the friction coefficient decreases with depth. So to clear this paradox, we ran out some simulation, some classical DEM simulation. So we use soft sphere with a Young modulus of 0.1 gigapascal with slightly polydispersed beads, and we use a classical linear spring dashpot model with a dissipation 0.88, and of course we use frictional particle and frictional wall, and we choose the same friction coefficient 0.5. So we just simulate a part of the flow, and we use periodic boundary condition in the direction of the mean flow. And contrary to the experiments where we fix the flow rate, here we fix the angle of inclination, and the system adapts itself the correct flow rate. So in simulation we vary the inclination angle, and also we can vary the gap between the wall. So first, result about the packing fraction profile throughout the system. So here, this is the free surface, and when we go, this is the depth, and we go in this direction, we go deep and deeper into the pile. So we have a great variation of the packing fraction. We start from a zero packing fraction, and when we go into the pile, it increases up to maximum value of 0.6. And we have different curves for different inclination angle. And we can see that the region where the fraction varies increase with the height, with the inclination angle. So we can reasonably well approximate this profile by a tangent, hyperbolic tangent function, where a length scale appears here called L nu, which characterizes the depth over which the packing fraction varies. And if we replot this profile using the rescale depth, the depth rescale by this new length L nu, and the packing fraction rescaled by the maximum packing fraction. So we have an apse collapse here. And we obtain the following scaling law for this length scale, which is very linearly with the tangent of the inclination of the hip, and also proportional to the gap of the width. Here are the result of the simulation, linear scaling law with tangents. So this equation reminds us the scaling, the SSS equation. And we see that this length scale, L nu, is related, in fact, to the height of the flowing layer. And we will see that in the next slide. Here, these are the velocity profile. So we start from the free surface here, and we go deep and deeper in the pile in this direction. So these are a profile for different inclination number, and we can distinguish three different zones. Near the free surface, we have a region where the velocity is almost uniform and sometimes decrease. And then we have a nice linear region where the profile is linear, and then an exponential decrease of the velocity. And you can note that in the linear region, the shear rate is almost constant and independent on the inclination of the flow. And we can use the same scaling as for the packing fraction. If we rescale the depth by this length L nu and the velocity by the maximum velocity, we get also an apse collapse, except for the flow near the jamming angle. And this means that the region where the velocity profile is linear is of the order of this length scale L nu. So we can define unambiguously the height of the flow just by saying this is a fraction of L nu. We choose 2 L nu. And the more important feature to try to solve this paradox is to calculate the sidewall friction. So we calculate numerically from the numerical simulation. So we just call tau as the resultant friction force exerted by the wall on the flow. And we call phi the angle of this friction force, the angle with the main direction of the flow, phi. And we define a resultant friction, mu, as a ratio of this friction force to the pressure, the lateral pressure. And this is the result. This is the friction, the effective result, wall friction, resultant wall friction, as a function of the depth. And as you see, the friction is not constant. It varies throughout the flow. And you have a region here where the friction is almost constant, and this value is 0.5, is the microscopic value used in the simulation. And then the wall friction drastically decreases as a function of the depth. And in this region, the effective friction, if we plot the inverse of the effective friction, is the scale linearly with the depth. That is, it decreases inversely proportional to the depth. So this is the striking feature. The effective friction decreases as we go deep into the problem. So why? But from this result, we can now solve this paradox. So I skip this because I've only a few time. So we can rewrite the momentum equation and just release the two constraints you use. The uniformity of the packing friction. We've seen that the packing friction varies across the depth. We've also seen that the effective wall friction varies across the depth. So rewrite the equation. We can calculate the ratio of the stresses at a given depth. This is the rescale depth, but this length L nu. And we have the tangent of the inclination minus the contribution of the wall friction. And here we end up with the microscopic friction used in simulation, the ratio of this length L nu divided by the gap, and a function f of zeta, which is nothing but the integration of the resultant friction on the wall times the pressure. And the pressure here is not linear with the depth because we have a non-uniform. This is just the integration of the hyperbolic tangents. But the important consequence, as the effective wall friction decreases for large depth, this function remains a constant for a large depth. So this ratio remains positive, and we can plot this ratio, the ratio of the stresses as a function of the depth. And we see the first thing, so it remains a positive, and we see the existence of the focal points where the ratio is independent of the inclination of angle, and also we ran several simulations from different gaps, independent of the gap. So at this point, the ratio is invariance of the stresses, and we can write down the balance equation. So at this critical depth, we obtain that this ratio, which is invariance, is equal to the tangents of the inclination time this quantity, which is the effective friction at this critical depth. And we recover the SSS equation. So we can several questions can be addressed as this focus point has a real physical meaning. So we speculate that this critical depth can be interpreted as a transition between a liquid phase and a gassy phase. But we have no strong evidence for the moment for this. This is pure speculation. But the last point, just to to understand why this effective friction coefficient decreases with depth. So we investigated the motion of the grain deep into the pile, and instead to do some simulation which are very time consuming if you want to study precisely the motion of the grain in the static phase because they are moving very slowly, we turn to experiment, and this is an example of the motion of a grain deep into the file. And you can see the motion here. See, we have a kind of cage motion, and we have sudden jump here. And these jumps are very rapid, and these jumps are less and less frequent when we go deep and deeper into the pile. So two main conclusions. While the particles are trapped, they exhibit a rather random oscillatory motion with a zero mean displacement. And this gives that the contribution during this cage motion of the residual force is reduced to zero. So the contribution of the friction force is only due to this quick jump, where we have a net motion of the grain. So as the trapping duration grows with depth, the resultant friction weakens as we go deep into the pile. I think I will stop here. Thank you for your attention.
I have rather remarked in a question. Your SSH equation has appeared already in papers by Savage and myself and by Koch and myself in the year 1990, exactly the way you have stated it.
Yeah.
And with experiments there.
Yeah, I know. I know you were.
Your analytical expression for friction.
Yeah.
I assume that if you have a certain vertical pressure, the lateral pressure is the same.
Yeah.
Which it's not in a bulk solid.
Yeah.
There's a ratio between those, what Oscar was talking about the other day, which typically is round about 0.6 or 0.4 to 0.6.
Yeah, it's not exactly
in the static layer.
Yeah.
It will be higher in the flowing layer, closer to unity, but still not unity. I wonder how that might affect the model.
We measure, to do the calculation, we assume isotropic pressure, but we can calculate it, and it's almost isotropic. It's a ratio between it's 0.9 or 0.95. So it's a reasonable assumption to state that the pressure is isotropic, even in this narrow.
In the flowing layer?
In the flowing layer, even in the pile.
Static layer?
In the static layer also.
So you've measured the outward force on
Yeah. We measure it.
And you found a K?
I can't remember exactly, but it's rather tropic. This approximation is quite valid.
Okay.
I can show you in more detail the result.
Interesting to see.